Good evening, everyone. So today in this session, we'll be starting with the atoms and nuclei. So the first session will be discussing about the atoms, right? We'll be discussing about the different models of atom. We'll be starting with Thomson's model, and then finally we'll be dealing with the Bose model of atom as well, right? So starting with the different models of the atom, the basic model that was given by the Thomson, right? It was a very simple model given for the atom, right? In which he said that an atom consists of positive charge as well as negatively charged matter, right? Both negatively charged as well as the positively charged matter, right? And this positively charged metal is actually distributed like a sphere, right? Atom he considered as a spherical charged ball, right? And this positive charge is uniformly distributed within the volume of this sphere, right? And within this volume, there is a distribution of electron as well, right? So it was a very basic and fundamental uh, distribution, right? Or we can say it was a very basic model given by the Thomson, right? And he said that an atom is an electrically neutral, right? And an atom is like a sphere which is electrically neutral, right? And positively charged, it's actually distributed inside this sphere up to a radius of this 10 to the power minus 10 meter, or we can say 1 angstrom, right? In which electrons are embedded, right? And within this positive charge, their electrons are embedded within the volume of this sphere, right? So this was a very basic model, right? But there were immediate shortcomings to this model, right? Uh, the important shortcomings to this model were that it could not explain the spectrum of atoms, right? We recorded the spectrum of different wavelengths during that time, right? Which could not be explained because of this model, right? So it was a very restricted model for the atom, right? And also it could not explain the scattering of particles like alpha particles. So this model also could not explain very basic and fundamental observations, that was the spectrum as well as the scattering of particles, right? So it was a very basic and confined model of atom given by Thomson, right? Later on, to correct all these shortcomings, another model was put forward by the Rutherford, Geiger, and Marsden, right? These were the three people which put forward the new model, which is called as Rutherford's alpha particle scattering experiment, right? So they were actually the three persons, right? Geiger, Marsden, and Rutherford. Geiger and Marsden were the students of Rutherford, right? So they together actually put forward a different model, a new model, and tried to correct the shortcomings of the Thomson's model of atom, right? So with respect to the Rutherford model, right, what this model was exactly. So it was an experimental setup, right? It was an experimental setup where we have the lead box, and inside this lead box container, right, we are keeping a source of alpha particles, right? Source of alpha particle, right? Like polonium. Polonium is an element, right, which emits the alpha particles, right? Let's suppose polonium has been kept inside this lead box, right? And there is an orifice, right, or hole, very pin hole in this lead box, right? Which through which a collimated beam of alpha particles comes out, right? Collimated beam of alpha particles comes out, and we have then here on this side we have the gold file here, right? And these alpha particles strike the gold file, right? And then we also have the zinc screen, right? Zinc screen and the microscope in this setup, right? And this setup is actually placed in a vacuum, right? Vacuum is created for this setup, right? And there were different observations with respect to this setup. So what were the observations? So this microscope or this zinc screen actually can rotate, right? This can rotate from above to the below, right? Continuously, right? So alpha particles, actually collimated beam of alpha particles are scattered, or this is the source of alpha particles. Collimated beam of alpha particles strike this gold foil, right? Strike this gold foil, and there were certain observations. What were the observations? That once we move this zinc sulfide screen from up to down, the specialty about the zinc sulfide screen is that whenever a particle, right, strikes the screen, it creates a bright flash, right? On the screen, right? Whenever a particle or alpha particle or any other particle strikes the screen, it creates a flash, bright flash. and that bright flash could be seen with the help of microscope. So that's the reason we are putting a microscope over the screen of this zinc sulfide, right? So experiment was about we are scattering or we're striking the alpha particles on this gold file, very thin gold file, right? So it was observed that actually very few particles collided with the atom of the foil, right? And most of the particles actually passed through this gold foil, right, without any deflection, right? It means that most of the intensity of the alpha particles were observed like this, right? Where there is no deflection. So at this point, the maximum deflection, maximum intensity of the alpha particle was observed. It means that so at this point there is no deflection, right? Straight to this point, there is no deflection. It means that the intensity of the zinc sulfide screen will be bright at this point. It means the maximum of the more than 90%, or we can say 99% of the alpha particles actually pass through the atom, right? So few alpha particles were, some flashes were observed at an angle of theta, right, on this zinc sulfide screen. Some bright flashes were observed on the zinc sulfide screen at an angle of theta. It means there are few alpha particles which were deflected by this angle of deflection, that's theta, right, and that were recorded on this zinc sulfide screen when the bright spot was observed through the microscope, right, on this sulfide screen. So similarly, it was also observed that there were also few particles which actually continue, which got deflected from this gold file, right? They retraced their path, right? They retraced their path. It means that when alpha particle retraced their path, it means that there is a strong deflection observed by these alpha particles, right? And that's the reason they suffered a 180 degree of deflection, right? So, since most of the alpha particles pass through this gold file, it means that actually the most of the atoms of this gold file actually they're like an empty space, right, inside this gold file, right? It means that he concluded that most of the space of this uh, alpha particle, not alpha particle, of these gold atom are actually the hollow spaces, right? These are the hollow spaces. And because of the strong deflection of alpha particle where they actually retrace their path, it means that there is some hard, where there is some substance at the center of this atom which produces the maximum deflection of 180 degree, and that center of that atom he called as the nucleus of atom. So we can say that actually through this experiment, uh, nucleus of an atom was detected, and alpha particle can only be scattered scattered with such strong deflection when there is a equal amount, or we can say there is a positively charged part of this atom at the center of this atom, right? Or we can say that nucleus of an atom is a positively charged space, right? So entire positive charge was almost wholly concentrated in small center that was called as the nucleus of an atom, right? So there were deflections there were zero deflections for most of the alpha particles. There were some deflections at an angle of theta, right? Slight deflections. And there were some particles which were deflected at an angle of 180 degree, right? It was because, or we can say there was a head-on collision between the nucleus of an atom, right? Nucleus of an atom and the alpha particle, right? So from this experiment, Rutherford detected the nucleus of an atom, right? And he said that he also observed that alpha particles are not deflected by the electrons because of their very less mass, right? They're particles of very small masses. There was not much uh, deflection observed with respect to the electrons, right? Because of the electrons in the alpha particles, right? So observation was that he concluded the electrons revolve around the nucleus in circular orbits, right? So he proposed a new type of model of the atom, where he said that the positive charge of the atom, instead of being uniformly distributed throughout a sphere, as in case of Thomson's model, he said this positive charge is actually concentrated in a very small space or volume, right? Whose diameter is less than 10 to the power minus 13 meters, right? It's of the order of femtometers, right? At its center, right? And this central core he called as nucleus, and nucleus is surrounded by the cloud of electrons, right? Which revolve around the nucleus in circular orbits. So this was the model put forward by the Rutherford. So he actually corrected the concept of Thomson that electrons are not like embedded in the uniformly distributed positive charge in a sphere, right? Actually, positive charge is concentrated in a very small space that he called as nucleus, and around that nucleus there are the electron clouds, right? So that was the correction done by the Rutherford, right? So later on, once again, this Rutherford's atomic model could not explain the stability of atom, because we know that whenever a charge moves around the nucleus, right, it is an accelerated system, right? It's an accelerated system, so it must lose its energy, right? It must have the definite energy, right? So so the stability of atom was not explained by the Rutherford's model, right? And it also could not explain the hydrogen spectra, right? It could not explain the discrete nature of the hydrogen spectra, right? So to explain this hydrogen spectrum, there was put forward another model that was given by the Bohr, right? That was that was given by Neil Bohr. So these were some of the important shortcomings to this model as well. That's the Rutherford's model of atom, right? Rutherford's model of atom. Then came the then Bohr's model of atom was introduced, right? Particularly Bohr's hydrogen model of atom, right? Now, let's talk about the Bohr's model of hydrogen atom. What Bohr said that he said that for a hydrogen or hydrogen-like species, right? Or we can say for a monoelectronic system, right? We can have hydrogen, uh, we can have a helium positive, right? Or we can have a lithium 2 positive atom, right? So these are the monoelectronic systems, or the atoms having single electrons, right? So Bohr's model says that electrons revolves around the nucleus of an atom because of the mutual attraction, electrostatic attraction between the nucleus of an atom and the electron, right? And that because of that mutual attraction between the nucleus of an atom and the electron revolves around the nucleus of an atom in a circular orbit, and these circular orbits are having the fixed energy, right? He called these orbits as stationary orbits, right? So these are the orbits of fixed energy, right? It means that unless and until this electron is in this orbit, it neither will gain the energy or it will not lose the energy, right? So these orbits were called as the circular orbits, right? Now another point is that with respect to the hydrogen Bohr's model, the first point is that electrons revolve in circular orbits, right? Electrons revolve in circular orbits of fixed energy. Circular orbits of fixed energy. The second point was that only those orbits were permitted in hydrogen atom which has the angular momentum equal to integral multiple of h upon 2 pi, right? Integral multiple of h upon 2 pi. So he said that the orbits are not the continuous orbits. These are the discrete orbits. He said that the energy of an electron is not a continuous energy here. The electron possesses the discrete energies, right? It means that all values of energies are not possible for this electron, or we can say that all values of angular momentum for this electron are not possible. Only the discrete value of angular momentum are possible for this electron, or we can say the orbits are the only discrete orbits are allowed, right? So he said that the angular momentum of electron, that's equal to mvr. Let's suppose if electron is moving with the speed v in a circular orbit of radius r, then mvr will be the angular momentum of this electron about this center, right? That has to be equal to the integral multiply of h upon 2 pi, right? H upon 2 pi, where h is nothing, h is the Planck's constant, right? H is nothing, that's the Planck constant, right? H is a Planck's constant, and the value of this Planck constant is nothing, it's 6.63 into 10 to the power minus 34 joules second, right? Joule second, right? So Planck constant actually represents the angular momentum, right? It's an angular momentum, right? So mvr is equal to nh upon 2 pi. So only integral multiples of angular momentum are possible, or we can say only those orbits are permissible here in this model, which has the angular momentum equal to integral multiple of h upon 2 pi, or we can say that if L is the angular momentum, only orbits of angular momentum h upon 2 pi, right? H upon pi, 3h upon 2 pi, 2h upon pi, right? 5h upon 2 pi, and so on, So these electrons, these orbits are only possible, right? So n can have values, right? 1, 2, 3, right? And so on. So these are the possible values of the angular momentum or orbits for this hydrogen atom, right? And the energy of these orbits in electrons are actually fixed, right? And the last point about this hydrogen atom is that where he explained actually the different spectra, right? Different spectra. He said that when an electron jumps from lower energy orbits to higher energy orbits only when it absorbs some energy, right? When an electron absorbs some energy, it jumps from lower energy orbits and higher to higher energy orbits, right? And the energy required for this transition from lower energy orbits to higher energy orbits is actually equal to the energy difference between the two orbits, right? It's equal to the energy difference between the two orbits, right? That's equal to E2. Let's suppose E2 minus E1, that's equal to delta E, right? It means that the electron will make transition only from lower energy orbits to higher energy orbits if it absorbs an energy equal to the energy gap between the two orbits, right? So if any energy is given less than the difference between the two orbits, energy difference between the two orbits, the electron will not make any transition at all, right? It will not make any transition at all. So similarly, if an electron is at higher orbits, right? And electron if electron makes a transition from higher energy orbit to the lower energy orbit, right? So it will release an energy in the form of a radiation equal to the energy difference between the two orbits, right? So these were some of the postulates or points of Bohr's model of hydrogen atom, right? And with the help of this Bohr's model of hydrogen atom, we could actually calculate the radius of radius of an electron orbit, right? We could calculate the velocity of electron. We could calculate the total energy of the electron, right? So we could calculate different factors of an electron, right? And we could also explain the hydrogen spectra, right? The discrete wavelengths are emitted when an electron make a transition from higher energy level to the lower energy level, right? So we'll be studying that later on. So the important point with respect to the Bohr's model is that electrons revolve in circular orbits of fixed energy, and only those orbits are permitted whose angular momentum is integral multiple of h upon 2 pi, and the electron makes a transition from lower energy to higher energy only when an electron absorbs an energy equal to the energy gap between the two orbits, and the electron makes a transition from higher orbit to the lower orbit, then the equal amount of energy is actually emitted in the form of a radiation, right? That energy of that radiation is actually equal to the energy gap between the two orbits, right? So let's do the calculation with respect to the radius of orbit and the velocity of revolving electron, right, in an orbit, right? Let's suppose let's suppose this is an hydrogen atom, right? And this is the nucleus of an hydrogen atom, right? This is a nucleus of an hydrogen atom, and we know that in the nucleus of an hydrogen atom has the atomic number 1. Z value of the hydrogen atom is equal to 1. It means that in the nucleus of this hydrogen atom, there is only one proton, right? There is a one proton and zero neutrons, right? So there is no neutron in an hydrogen atom or in the nucleus of an hydrogen, and it has got one electron which is revolving around the nucleus of an atom according to the Bohr's model, right? According to the Bohr model. And let's suppose the radius of this uh, orbit. Let's suppose this is an nth orbit, right? This is an nth orbit, right? It can have uh, there are infinite number of orbits possible for this electron. Let's suppose the electron is present in the nth orbit, right? And the radius of this nth orbit is Rn, right? Rn is the radius of this nth orbit, and the speed of this electron in the nth orbit is Vn, right? Vn. Now the electron is moving around the nucleus, right, in a circular orbit. It's only because when the necessary centripetal force is provided by the electrostatic force of attraction between the nucleus and electron, right? Between the nucleus and the electron. So electrostatic force of attraction between the nucleus and the electron is nothing that's given by the Coulomb's law, right? That will be K, right? K Q1 Q2 upon R square, right? Now here we can see that the charge of a proton here is equal to the charge of electron. That's E, right? Right? And so it will be Ke square, right? Ke into E upon R square, or we can write Rn square for the nth orbit, right? So this will be equal to mv vn square upon rn, right? Where rn is the radius of nth orbit, right? Rn is the radius of nth orbit. We can use the second postulate of Bohr's model. That's the angular momentum is quantized, or we can say that v mvn rn has to be equal to nh upon 2 pi, right? nh upon 2 nh upon 2 pi. So from here we can see here, from here what we can do is that we can just cancel out this r and r here, or from here we can conclude that it should be equal to e square. We can put the value of k equal to 1 upon 4 pi epsilon naught, so it will be 4 pi epsilon naught rn, right? That will be equal to mvn square, right? Now we have to calculate the value of r, right? If we have to calculate the value of r, we can just replace the value of v in terms of the value of r to calculate the radius of this nth orbit of a hydrogen atom, right? So Vn will be equal to nh upon 2 pi m into Rn, right? So this will be the velocity Vn of the electron in the nth orbit, right? So now we can plug in this value of this velocity in this equation, right? We will get the value of radius. So E square upon 4 pi epsilon naught Rn m Vn square. So we can replace Vn square by n square h square upon 4 pi square m square, right? Rn square. So Rn and Rn will get cancelled from here. We'll be left with value of Rn as this is the radius of electron orbit, right? Nth orbit of an electron. That's Rn is equal to n square h square, right? M and M will get cancelled, right? We'll be left with n square h square upon 4 pi square, 4 pi square multiplied by 4 pi, right? Just a minute. So Rn will be equal to, so we'll just take the Rn, this in the numerator and this in the denominator. It will be n square h square, right? Upon 4 pi square me square and multiplied by 4 pi epsilon, right? 4 pi epsilon. Now from here, 4 and 4 will get cancelled, pi and pi will get cancelled. We'll be left with n square h square, right? Epsilon naught upon pi me square. So this is the radius of nth orbit of an electron, right? In a hydrogen atom, right? So according to Bohr's model, this will be the radius of nth orbit, right, in an hydrogen atom. And you can see there, h value, h is the constant here, right? H is the Planck's constant, right? It's a constant. Epsilon naught is the permittivity of free space, right? It's also a constant. Pi is constant. Mass of electron is constant. And the charge of electron is constant, right? So these are all the constant values here, right? So if we calculate the values of these constants here, so h square epsilon naught upon pi mv square, this comes out to be equal to 0.53, right? 0.53 angstrom, right? 0.53 angstrom. Or we can write the radius of an orbit, nth orbit of an electron, Rn, that's equal to 0.53 multiplied by n square, right? Multiplied by n square. So this is the radius of an nth orbit of an electron, right? This is the radius of nth orbit of an electron. Now, this is with respect to the hydrogen atom only, right? Now, let's suppose that we have the monoelectronic systems. We can have helium positive, we can have lithium 2 positive, right? So for those atoms or for those systems, right, which are monoelectronic, right, the hydrogen model can still be applied, but in that case, the value of Z will change, right? Value of Z will change. For helium, the value of Z is 2, and for the lithium, the value of Z is 3. So there will be slight modification in this equation for the calculation of the radius of an orbit, right? So if we see here, we use the Coulomb's law here, that was K E square upon Rn square, right? So it means the total charge for the hydrogen helium will be here, it will be equal to 2ice, right? Similarly, the total charge at the center of this nucleus for the uh, lithium will be 3 times E. Or in general, we can say we can replace here in this equation, we could replace the value of charge here with the Z times E, right? When we replace here the value of charge here by Z times E, right? So what we'll get here, it means it will be equal to Rn, that will be equal to 0.53 multiplied by n square, right? So that will be mv square. So it will be n square upon z, right? We'll get a factor of z here, right, in the denominator, right? So in general, we'll get a factor of z here. So it means for any monoelectronic system, the radius of nth orbit of an electron for any monoelectronic system, it should be equal to 0.53 multiplied by n square upon z in the units of angstroms, right? In the units of angstrom, right? So for the first Bohr orbit, right, of hydrogen atom, the value of radius of an electron or radius of an orbit of electron is 0.53 angstrom, right? 0.53 angstrom. Similarly, we could calculate the velocity of electron as well. Now, if we substitute the value of radius back into this equation, we'll get the value of the velocity of an electron, right? Value of the velocity of an electron, right? So the velocity of an electron in the nth orbit will be equal to velocity of electron in an nth orbit, that will be equal to 2.18, right, into 10 to the power 8 meter per second, right, in the units of meter per second, right? Or we can directly derive it from this equation here as well, right? So we can just establish the dependence of this velocity of an electron on this quantum number, principal quantum number n, right? So value of r was here n square h square epsilon naught upon pi mu square, right? We can put the value of r here in this equation to get the value of vn, right? To get the value of vn. So value of r comes out to be equal to rn, that's equal to n square h square epsilon naught upon pi mu square, n square h square epsilon naught upon pi mu square, right? So this is the value of radius, right? And we know this equation, we can use this equation, right? This equation, let's use this equation. So from this equation, e square upon 4 pi epsilon naught rn, e square upon 4 pi epsilon naught rn, that's equal to mvn square, right? Mvn square, right? Now substitute the value of rn in this equation, we'll get e square upon 4 pi epsilon naught. The value of rn is n square h square epsilon naught multiplied by pi m square here, right? That will be equal to m vn square. Now here you can see that actually the velocity is independent of the mass of electron, right? It's independent of the mass of electron, right? Now, so this is the value of velocity of electron, right? Pi and pi will get cancelled, right? And now you can see here it's e square, right? Or we can say it's e to the power 4. It's epsilon naught square, it's 4n square h square epsilon naught. So from here, vn will get the value of e square, right? E square upon 2 epsilon naught, right? H upon n, right? So this is the value of the velocity, right? This is the value of velocity of electron in the nth orbit, right? Or we can say that the value of this e square upon 2 epsilon naught h is nothing, it's 2.18 into 10 to the power 8, right? Multiplied by this factor 1 upon n, right? So this is the dependence of the velocity of electron in its nth orbit, So Vn has the value of 2.18 into 10 to the power 8 multiplied by factor 1 upon n. So n is nothing, is the principal quantum number. N is principal quantum number. N we call here as principal quantum number. So it means that as the value of n increases from this equation, the velocity of the electron in an orbit is going to decrease, right? Similarly, as the value of n increases, the radius of the orbit is going to increase, right? So it means that when the value of n tends to infinity, the electron actually has the kinetic energy equal to 0, right? For n equal to infinity, it means that the electron will be detached from the atom, or this will be an electron will be in an unbound state, right? It will be unbounded from this hydrogen atom, right? As n tends to infinity, right? Now, talking about the energy of the electron, now electron has the two types of energy, right? Mechanical energy here. One is the kinetic energy, and another is the potential energy. So these are the two energies possessed by this electron, right, in this hydrogen atom. So sum of both these energy will correspond to the total energy of this electron, right? So we can just write here the electronic energy here will be nothing. It will be the total E total, that will be equal to the kinetic energy of this electron, right? that will be equal to kinetic energy of electron plus potential energy of this electron, right? So it will have kinetic energy as well as the potential energy. And the kinetic energy, we know it's half mv square, right? And that's equal to half mv square. And potential energy is the electrostatic potential energy, right? For this electron, right? Now let's write the value of kinetic energy. We know mv square upon r, right? Mv square upon r, that's equal to nh upon 2 pi, right? Nh upon 2 pi. That's nothing. That's what we call as that's equal to that's the mv square upon that will be equal to the electrostatic force, right? Or we can say mvr has to be equal to nh upon 2 pi. So mv square upon r will be equal to ke square upon, right? Ke square upon r square, right? R and r will get cancelled now. So if we multiply by a factor of half on both sides of this equation, so half mv square is nothing. This will be the kinetic energy. So kinetic energy is nothing. That is equal to k square upon 2r, right? K square upon 2r. So it means that k square upon 2r. And we know the potential energy possessed by the potential energy possessed by this electron, right? If we calculate the potential energy will be nothing. It will be electrostatic potential energy here. So the potential energy will be equal to k q1 q2 upon r, right? And the charge of electron, it's a negative charge, right? It will be minus k, right? E square. And taking the positive charge of proton of this atom, right? But the magnitude will be equal to E only, right? So it will be minus K square upon R, right? Now you can see here, uh, K square upon R is nothing. It's equal to minus times potential energy, right? K square upon R is equal to minus times potential energy, right? Or we can say here, the kinetic energy is minus PE upon 2, right? It's minus PE upon 2, right? So this is the value of kinetic energy here, right? K square upon 2 will be the value of the kinetic energy here. So if we put the value of K here, that will be equal to E square upon 4 pi epsilon naught multiplied by 2R, right? Multiplied by 2R. And the value of the radius, we know that's n square h square upon, epsilon naught upon pi m square. We can put the value of R here. So it will be E square upon 4 pi epsilon naught, right? Multiplied by 2 and r has the value n square h square epsilon naught upon pi m square, right? Pi m square. So pi and pi will get cancelled, right? So we'll be left here with kinetic energy value equal to, that will be me4, right? Me to the power 4, right? Upon 8 epsilon naught, upon 8 epsilon naught, right? N square, 8 epsilon naught square, right? It will be 8 epsilon naught square, n square and h square, right? So this will be the kinetic energy, right? This will be the kinetic energy. And the potential energy will be equal to, potential energy of this electron will be equal to PE, that's equal to minus K E square upon R, right? Minus K E square upon R. That will be equal to minus E square upon 4 pi epsilon naught into R. The value of R is n square h square epsilon naught upon pi m square, right? So n square h square epsilon naught multiplied by pi m square, that will be in the numerator, that will be pi m square, right? So it will be equal to minus pi and pi will get cancelled here. It will be minus me to the power 4, right? Me to the power 4 upon, it will be 4 times epsilon naught square, right? N square h square, right? N square h square. So you can see here, this will be the value of the potential energy. And the sum of kinetic energy plus potential energy will give us the total energy, right? So E total will be kinetic plus potential energy, right? K plus P. So value of P is me4 upon 4 epsilon naught square, N square, h square. And that value of the kinetic energy we got it. That's me4 upon 8 epsilon naught square, N square, h square. So me4, right? me4 upon 8 epsilon naught square, N square, h square. 8 epsilon naught square, n square h square, right? So the total energy will be the negative energy for this electron, that's Me4 upon 8 epsilon naught square n square h square, right? N square h square. So this is the total energy of this electron in its nth orbit, right? In its nth orbit, the total energy of the electron is nothing, that's equal to minus m e to the power 4, right? M e to the power 4 upon 8 epsilon naught square n square h square, right? Now you can see here the mass of the electron is constant, charge of electron is constant, permittivity is a constant, and Planck's constant, it's a constant also, right? So if we calculate the values of these constants, m e to the power 4 upon 8 epsilon naught square, right, h square, the value of this constant comes out to be equal to minus 13.6, but in the units of electron volt, right? In the units of electron volt. So total energy of the nth, in the nth orbit of electron, right, that will be equal to minus 13.6, right? So minus 13.6, right? Minus 13.6 multiplied by 1 upon n square, right? 1 upon n square. So this is the energy possessed by the electron in an hydrogen atom in its nth orbit, right? So you can see here the total energy is negative, right? It means that this electron is bound to this atom, right? It's bound to this atom, right? So it means that in order to unbound this electron from this atom, we have to supply at least this much of minimum energy to unbound this electron from this atom, right? That's what we call as binding energy, right? Binding energy. So binding energy is nothing, right? Binding energy, right? So binding energy will be equal to, that will be equal to plus 13.6 multiplied by 1 upon n square, right? So this much of energy will be required for an electron to unbound from this atom, or to knock this electron from the atom to the infinity, right? So there will be no influence of this hydrogen atom on this electron. So this energy we call it as binding energy or ionization energy as well, right? We call it as binding energy or ionization energy as well. So total energy is minus 13.6 into 1 upon n square. N is the quantum number, right? Principal quantum number, right? Orbit number. And binding energy is plus 13.6 into 1 upon n square, right? Now, talking about the total, you can see here, actually the total energy is actually negative times the potential energy, right? Or negative times the kinetic energy, right? You can see here, E total, right? E total energy is actually equal to minus times kinetic energy, right? Minus times kinetic energy, right? Minus times kinetic energy. So total energy of this hydrogen atom, of this electron in a hydrogen atom, is minus times kinetic energy. And the value of kinetic energy, right, and potential energy, you can see here, if this is equal to, total energy is equal to minus times kinetic energy. So E total, we know that's equal to Ke plus Pe, right? Or you can say minus Ke, that will be equal to Ke plus Pe, right? So from here you can see that potential energy will be actually equal to minus kinetic, half of kinetic energy, right? It will be minus times half of kinetic energy, right? The potential energy will be equal to minus times half of kinetic energy, or minus 2 times kinetic energy, not half, minus 2 times kinetic energy. So this will be the value of the potential energy, right? This will be the value of potential energy, right? Now let's talk about the different energy levels in an hydrogen atom, right? We calculate the value of total energy in a hydrogen atom, right? That's equal to minus 13.6, right? Minus 13.6 into 1 upon n square, right? Into 1 upon n square. So this is for hydrogen atom, right? For Z equal to 1. This is for Z equal to 1, right? This is equal to, this is for Z equal to 1, right? Now the question is that for any other monoelectronic system, the value of Z will not be 1. It in general can be taken as 1, right? So if we substitute the value of Z in these equation, we will get a factor of Z square in the numerator. So it means that the total energy for any monoelectronic system, right, will be equal to minus 13.6 into z square upon n square, right? Into z square upon n square, right? So this will be the total energy of an electron for any monoelectronic system. That's z square upon n square, right? In the units of electron volt, right? In the unit of electron volt. Now you can see here energy is actually inversely proportional to the n square, right? It means as we move to the higher orbits, right, or higher energy levels, the energy of the higher energy levels, or we can say higher orbits for higher n values, the energy is more, right? The energy is more, right? So energy actually increases, right? So it means that, let's suppose this is the hydrogen atom and these are the different energy levels, right? These are the different energy levels. These are the different energy levels. So for n equal to 1, if we put the value of n equal to 1, the E1 will be equal to minus 13.6 electron volt, right? Minus 13.6 electron. For n equal to 2, the value of the energy is minus 13.6 upon 4. That will be equal to minus 3.4 electron volt, right? And similarly for n equal to 3, we'll have the E3 value that will be equal to minus 13.6 upon 9, right? That will be approximately equal to minus 1.51 electron volt, right? And similarly for n equal to 4, the value of energy E4 will be equal to minus 13.6 upon 16, right? That will be equal to minus 0.85 electron, right? So you can see here, as the n tends to infinity, the total energy of the electron becomes equal to 0, right? So the total energy at infinity for this electron is equal to 0, right? So here the electron will be unbound from the system, right? So you can see that as we move up, the energy gap between the two energy levels actually decreases continuously, right? It continuously decreases, right? So the maximum energy gap will be between n equal to 1 and n equal to 2. There will be a maximum energy gap, but the energy gap between n equal to 2 and n equal to 3 will decrease, and the energy gap will further decrease between n equal to 3 and n equal to 4, right? So for n equal to 1, if this is 13.6, right, minus 13.6 electron volt, right, then this will be the value equal to minus 3.4 electron volt. Now the gap between the energy level is going to decrease, right? So this will be the gap. Now this will be the gap. So that will be equal to energy level minus 1.51 electron volt. Now this gap will further decrease, right? This gap will further decrease. And this energy level will have energy equal to minus 0.85 electron volt, right? And this gap is going to further decrease till infinity, right? So it will continuously decrease, right? It will continuously decrease. So it means that energy levels become closer and closer to each other as the value of n increases, right? So the value of energy levels becomes closer and closer to each other as the value of n increases, right? So this is the energy of an electron in different orbits, right? And similarly, we also calculate the value of velocity, and this value of velocity, we found that it's actually independent of mass of electron, right? It's independent of mass of electron, right? So, and different orbits, the radius of the orbit actually increases with the value of n, right? And it decreases with the value of z, right? So, more the value of z, the value of radius will be smaller, or the orbit will be of smaller radius, right? So, in the next lecture, we'll be studying about the different spectral series, right? Different spectral lines, actually hydrogen spectrum, using these energy equations, right, of this hydrogen atom, right? So we'll be stopping here, and rest of the discussion will be done in the next class.